It's an honor to be here. Thank you. I have to acknowledge my co-author, Somdeep Ghosh. Into my work quite a bit when I was doing a sabbatical in IBM just about a year ago. My graduate student, who's still at Virginia Tech, Fatemeh Hashmi, and Peter Glynn at Stanford. Okay, so my talk today is titled Adaptive Sampling Controlled Stochastic Recursions. So I've been thinking about stochastic approximation in general for a little bit now, and the broad theme running throughout this talk is the following. I'm going to give a little more introduction to what stochastic approximation is all about, so as to provide some context for my talk. But stochastic approximation broadly is a way to solve what are called simulation optimization problems, and it's a recursion that has been used for over 6 decades now. And the way these recursions generally work is that they, in order to kill stochasticity or randomness that is observed in these problems, they introduce a sequence of parameters, which I'll introduce in a little bit. My whole contention in all of this is that instead of introducing a sequence of parameters, as in stochastic approximation, one can achieve the same effect by sampling, and by sampling carefully. And so this kind of started early on, a few years ago, in 2010, in a paper in operations research. And ever since, we've kind of worked on this topic, we've refined it a little further. But really, it is the second paper that is currently under revision in Science Journal on Optimization with the same co-authors. And the current one, which I'm going to talk about in a little more detail. Okay. So let me state the problem context in slightly greater detail. I mean, trying to minimize a function, a real-valued function f of x, subject to a constraint set. The key issue is that we don't know f well, so we are forced to run a simulator, so to speak, some Monte Carlo simulation. So we observe little f at a particular x by actually running the Monte Carlo simulation a little bit, and we get an estimate of capital F sub n. Right? And likewise, we do the same thing for constraints potentially. And so this is all we have. We don't observe little f and little g exactly. This is traditionally called the simulation optimization problem. There is a variation on the same thing for root finding, where instead of attempting to minimize little f, we're actually attempting to find the roots of, or the zeros of little f, so to speak. And that's called stochastic root finding. Lots and lots of applications. A recent application is, for example, in allocating vaccines. Whom do you give these vaccines to in order to minimize the expected total number of deaths, okay, or spread of a particular disease? So there, little f essentially is the expected number of deaths, and x is the allocation, the particular allocation that you're going to use for these vaccines. So you can't evaluate little f exactly, so you have to run a simulation in order to get estimates of little f. So this is a broad context in which we'll be thinking about things.
Just a quick question.
Yes.
It looks like you also don't know G. You're running a simulation on the constraints too. Is that right?
That's correct. That's correct. Yes. All right. So this question is not new. I mean, it was posed in 1951 by Robbins and Monro. He just didn't call it simulation optimization. They didn't call it simulation optimization, but they posed that problem and they created what has now become a very famous recursion. Xk plus 1 is xk minus ak times g of xk. G here, or this recursion, was for the root finding context. So you're not attempting to find the minimum, but instead the zeros of that function. Okay? And capital G is an estimate of little g. So this is the recursion that they introduced. And over the last 6 decades, amazing amount of development has happened on this recursion. Pretty much, I mean, if you come up with a question on the theoretical property of stochastic approximation that's not been studied, it's difficult to find a question of that sort. For example, I just before coming, I typed stochastic approximation in Google Scholar, and it gave me about 1.77 million hits. It's just quite stunning how pervasive this is. Stochastic approximation is enormous number of variations, more than 6 decades of research. So it's really I mean, there's no question on its popularity. convergence has been studied really, really well. It attains what is called the canonical rate. By canonical rate, what I mean is it attains the order 1 over root k convergence rate. So to give a little more intuition on this, for regular estimation, if you're trying to estimate a population mean, and if you estimate the population mean using a sample mean, we all know that the variance of the sample mean is order 1 over n. So the standard error drops off as 1 over square root of n for estimation. Now for optimization, hence, one can hope that you can do much better than that. In stochastic approximation, by the kth iteration, the total amount of effort is k. So if estimation itself can only give you order 1 over root n convergence or square root of work convergence, you can't do much better than this. And so the crowning achievement, so to speak, of Robbins and Monro was that they showed that algorithm was order 1 over root k. Okay? So ever since, all of the algorithms, generally try to match this rate, so to speak. Okay, so why do we even need to challenge this? What is the problem with stochastic approximation? Without going into too much detail, it's interesting how that question is answered depending upon the particular community you ask. If you go to the EE community, for example, they're really big proponents of stochastic approximation. It works for them, so to speak. And so you'll have a lot of backing towards stochastic approximation. There are other communities, particularly the one I come from, where lots of people have trouble choosing this gain sequence. This sequence basically in this algorithm tends to be really difficult to choose automatically. It's very hard to choose it. Of course, it has nice properties, and you know how to choose it at a broad level. You want to ensure that summation of AK diverges and summation of AK squared converges. But that's the level at which you know it. And there are many, many attempts. There have been attempts, even as recently as 2010, a really nice paper by Asaf Zivi and Mark Brody, who try to adaptively choose this. But it's really difficult, is what I think. A second issue is, nonlinear programming. Techniques in nonlinear programming, shouldn't that be exploited more fully? And thirdly, SA tends to be a sequential algorithm. So you need to think, when you're trying to parallelize it, you need to think a lot about how to parallelize it. Okay. So what has happened in the last couple of years is primarily driven by people from the deterministic side, at least the way I see it. Why not we just solve simulation optimization problems by employing your favorite deterministic recursion, say quasi-Newton or a trust region, and replace the unknown quantities in the recursion by their Monte Carlo counterparts. All right? This seems like a reasonable approach, and people have recently, this sort of way of doing things has really taken off recently as a competitor to stochastic approximation. Okay, so this is the world in which we will live, in the sense that we'll try and see what we can say about how to estimate, how to do the Monte Carlo estimation in a more careful way. Okay, so we need to put this in sort of a framework. And so the particular framework in which I'm going to be placing all of this is the following. Think of a deterministic recursion, your favorite deterministic recursion for root finding. I'm going to, again, for the purposes of this talk, limit myself to root finding. We have a recursion of the form xk plus 1 equals xk plus h sub k. So all of this has basically been subsumed into this object. So if you're thinking about a quasi-Newton, you have a derivative, all the derivative, the deterministic derivative estimates, and the observed value, all of this is hidden within this object. Right? So we think of this recursion, so to speak, as a recursion to solve your optimization problem. Of course, we don't know little h sub k, so why not think about estimating little h sub k using your object, capital H sub k. So what we see is we are saying, hey, this is what I would have used if I were doing deterministic optimization or root finding. So I'm going to mimic this, and I'm going to use this recursion, but I'm going to take this object, mimic it, replace it with its Monte Carlo counterpart. How will I construct it? All right. Now this introduces a little complication. The complication is hidden within this object right here, m sub k. The point is, how much do I sample at that particular point? Right? That becomes the major issue. And we have to contend with this issue of efficiency, because do I sample more, do I sample less, and how do I carefully do this? So that's broadly the question that we will answer as we go through the talk. All right, so to give you a little further intuition on how all of this is going to fall out, this is a two-dimensional plot. This is in the design space. I ran an example root finding problem. And what I did was I plotted sample size on the z-axis. Intuition would dictate that when we are really far away from a solution, when we think we are very far away from the solution, we should sample very little. Right? And as we are getting closer and closer to a solution, we think we should sample a lot. And it gives us the sense that if we do that, we probably will be efficient. But what is efficiency? How do we exactly do it? All of this is subject to, is a detail that we really need to specify. And so that's what we'll talk about here. Okay, so what schedule of sample sizes guarantees convergence in probability with probability 1? What is the best available convergence rate for a recursion with a given estimator quality? What schedule of sample size achieves the best possible convergence rate? And can a practical adaptive algorithm be devised to exploit these results? These two are the particular focus of whatever I'm going to say from here on. Okay, before I go further, because this population is somewhat diverse, I have to explain what efficiency means in the context of stochastics. All right, so let me start with so this is an aside, by the way. So I've kind of gone away now, and I'm trying to explain what efficiency is and convergence rate is. So let's take the simplest example of estimating the population mean. And let's say I do the usual sample mean, simple sample mean. I'm just doing Monte Carlo without I'm not doing quasi-Monte Carlo, it's naive Monte Carlo. So I construct my estimator of the sample mean, estimator of the population mean. This is the true quantity. We know from the basic statistics that this error is order 1 over square root of n. Right? We know that. Now, this cannot be beaten. You can't do any better than this without actually doing something with the way you're sampling. Okay? So this is called the canonical rate in this context. What you may not have seen is in the context of gradient estimation, if you ask the same question. So suppose I'm trying to estimate the gradient of a function, and the way I do it is, let's say, through finite differencing. So I go forward, I actually estimate the function value, I go backward, and then I compute the finite difference, and I get a value. Now, it so happens that the amount of sampling I do and the step size should be in balance. And if you actually choose your little s carefully, you can show that the best possible convergence rate is no longer order 1 over root m, but it actually drops to 1 over m raised to the power 1 over 3. You can't do better than this. So in the context of gradient estimation under naive Monte Carlo sampling, you can't do better than 1 over m raised to power 1 over 3. So this is really slow rate. There's the corresponding rate for forward differences. Yes?
Does it depend on how smooth G is, or something about Y, how far Y can be?
Yeah, that's correct. We are assuming that G has up to the second derivative.
And regardless how big Y could be.
So when you say how big Y could be, I'm not sure.
Well, I don't know, finite variance, for example, or something.
So you're talking about this Y?
Yep.
Okay. So I'm looking to identify the gradient at this particular point, at little x.
So,
right? So, and if I'm choosing this is an asymptotic result where little s is little o of m raised by negative 1 over 6. So as long as G is smooth.
So it has nothing to do with Y has a finite variance or not?
Oh, yeah. Y needs to have finite variance. Absolutely, yes.
Okay.
Absolutely.
Okay.
And for forward differences, you get the corresponding rate m raised by negative 1 over 4. It's even slower, so to speak. So, linking this back to what I started off with, we're going to show that whenever we talk about efficiency in our context, we're going to show that we achieve the canonical rate. The canonical rate is defined similar to this guy. We're going to show that the algorithms, we're going to declare victory if the convergence rate is order 1 over the square root of work, because even if in estimation you can't do any better than 1 over square root of work, it's reasonable to think that in optimization you can't do much better than that, because the objects you're getting are similar to that using estimates. Okay, so order 1 over square root of work is a key quantity that we're going after. Okay, so we have done some work in the past relating to such problems, and it so happens that you probably have already guessed this, but in a situation of this sort, whenever we think about this recursion right here, the amount that one needs to sample is closely tied to how fast this corresponding recursion is moving, right? And the error between these two guys, right? If I have a situation where my recursion is moving down really quickly, like a second order recursion, like a superlinear recursion, one would think that you have to sample more. Because this is a trade-off between structural error and sampling error. You don't want to sample so much. If, for example, you sample too much, it means that, and your structural error is way bigger compared to your sampling error, you're doing all the sampling for no reason at all. If your sampling error is really, really big, you're not sampling enough, because your structural error is already small, and by sampling you can actually gain from it. That's dominating. So it all comes down to managing the error between the structure due to this recursion and the object's quality, so to speak. Right? These two need to be kept in lockstep in order to get efficiency. So we have done some work along these lines in the past, and we came up with some results corresponding to this. And so what I've plotted here along the rows is the speed of the recursion that you're using, underlying speed, which is either sublinear, linear, and superlinear. And along the columns, you have the rate at which you're sampling. I've not told you what polynomial sampling is, but it's not crucial for the talk. But polynomial is slow sampling, medium, and high sampling. And what I've plotted is error rates. The crucial point of this slide is that if you're sublinear, or if you're linear, for example, it is good to do geometric sampling up until a particular point, up until a particular threshold. Past that, it's inefficient. It so turns out that it becomes inefficient. Okay? And for superlinear recursions, any geometric sampling is okay, and past geometric up to a particular threshold is okay, but past that you become inefficient, and below that you are always inefficient. So you have this little wedge where you are in an efficient region, so to speak, okay, on sampling. So this kind of gives us a sense of how to, balance structure in our recursion and sampling, but doesn't quite, again, completely give us a nice algorithm, because all of this is theoretical, so to speak. All of these are predetermined sequence of sample sizes. So the same sort of criticism that I levied against stochastic approximation can be levied here. All right? So what we are going after now is, can we actually construct an adaptive sampling algorithm to react to algorithm history to be developed? Can it be efficient in the sense just discussed? Okay, so adaptive sampling is what we are looking for. So let's go back and think about this in slightly greater detail. So I'm looking for an adaptive sampling scheme, and notice I'm flashing again the previous recursion, which is deterministic. And now what I've done is I've simplified this a little further for the purposes of the talk. And notice here that the little nk has changed to capital NK. So I want a random sample size at any particular point. And I'm trying to mimic the original recursion with the stochastic recursion. Capital H is an object that actually estimates little h. And the particular heuristic that I'm trying is the following. So let's focus on this guy for just a little bit. Now, let's forget nu of k for the moment, m raised to power epsilon for the moment, and let's just focus on this portion. Now, h sub k, this should be just h of xk, but h of xk is an estimate of little h. So this is the norm corresponding to h. This quantity right here, sigma hat divided by root m, is a measure of, is an estimate of the standard error of capital H. All right? So we are asking to make sure that the standard error divided by the object itself is less than a pre-specified threshold. So this should look like a signal to noise ratio to you. So this is your signal, and this is your estimated noise, so to speak, sigma hat divided by root m. And you want to make sure that sigma hat over root m divided by norm of h is less than c. And this should remind you of the proportional width confidence interval, so to speak. So as long as your signal is strong enough, you want to keep sampling until your sigma hat divided by root m falls below this particular threshold. All right? Now we'll talk about mu and m raised to the power epsilon in just a moment. But what is interesting about this rule is that Jorge Nocedal and his co-authors came up with a very similar rule from a completely different standpoint. For example, in the same context of simulation optimization, they show that if I'm working on the same problem, and if I define d as a negative h, so to speak, estimated gradient in this case, they show that as long as the error in estimating little h, which is given as the norm of capital H minus little h, is smaller than some c times capital H. So this is saying that the fraction error is less than 1. It can be shown that this direction is a descent direction. Okay, that's an easy calculation, so it turns out. So given that this is true, meaning that given that this is a descent direction, and if we, for example, say the expectation of h minus little h turns out to be the variance in a case where capital H is unbiased, you can actually estimate this quantity through the variance estimator. Right? So this quantity right here is the variance estimate. So this immediately gives you a way to estimate a descent direction, so to speak. It's purely from an optimization side. So from a stochastic side, we are thinking about the coefficient of variation or proportional width confidence intervals. And it has an interpretation from the deterministic optimization context as well. And so, this heuristic has multiple meanings, so to speak. You can come at it in different ways. Okay, so this we think is a way to get rid of your sequence of parameters that are actually there in stochastic approximation. Of course, I'm introducing another sequence that I'm calling an escorting sequence, and we'll come back to this in just one moment. It so turns out that this guy is not going to be very important in the asymptotic behavior of the algorithm. Notice here that everything is based purely on just an adaptive sampling rule. So the sampling adapts to whatever observations you've already seen. Okay, so we make some assumptions. These are typical assumptions that are there in simulation optimization. A2 and A3 are the analogs of strong convexity. I'm going to assume before I present results that X star is unique, and we have a way by which capital H is specified. So I won't go into too much detail on that. This, in some sense, should give you this equation right here, this way of splitting things should give you complete intuition on how the analysis is going to go. Now, I write zk as xk minus x star. So zk is the usual error in your iterator at the kth level. So I split zk as zk plus, or this zk plus 1, sorry about the typo again. This quantity right here comes from the usual deterministic recursion. And on top of that, I have a quantity associated with how well you sample little h. If you actually assume strong convexity and take expectations, you can split the total error at the end of k iterations, or k plus 1 iterations, into a structural error part. This is something that you will see in stochastic approximation or in deterministic optimization, plus a quantity associated with your sampling. All right? So this should be reminiscent of stochastic approximation. In stochastic approximation, in order to kill the sampling error, you simply put in constants. You simply put in your gain sequence. And I'm suggesting, or we are suggesting, me and my co-authors are suggesting, that this sampling error can be killed in another way by actually sampling so that at the kth iteration, the amount of error adds up to something small as you go further and further out. So at some level, it is asking for capital M such that these two are roughly in lockstep. Okay, so the first one is about, the first result is a vanilla result on almost sure convergence. This is again reminiscent of stochastic approximation. All that you need to do is, without even thinking about sampling, you can show that when nu k is satisfying a particular condition, summation of nu k inverse is less than infinity, this portion in the limit adds up to really nothing. Okay, so and this comes from Robbins-Sigmund lemma, or slight variations in the Robbins-Sigmund lemma, but this is not particularly interesting in the sense that that quantity right there, you're choosing your sample sizes so that it adds up to something very little asymptotically. So that's the almost sure convergence. This nu k sequence, which I'm calling the escorting sequence, the only role that it plays is it makes sure that it gets you to the vicinity of the root. Okay, and as you get closer and closer, it ceases to be binding, so to speak. It gets you close, and after that, this rule essentially takes over. The sample size rule takes over. So to that extent, it's not very important. It shows, it brings you close, and then lets go, so to speak. Okay, that's almost sure convergence. Now, when we go back to this equation right here, we want to relate the second moment of this error to the actual sample size that you're using. We can relate that, and that is this result. It so happens that you can show that the second moment of this object that you're estimating or getting is of the order of the expected inverse of the sample size with an inflation. Let's not worry about this inflation. I'll come back to this in just one moment. These two are tending to a constant. So in other words, what we are really seeing here is if we go back to this equation, this quantity right here looks roughly like expected value of the inverse of the sample size is what that theorem is saying. Okay, so again, if you're losing intuition, this is essentially like in the vanilla estimation case, the squared error is of the order of 1 over m. And in this case, because the sample size is itself random, this looks like expected 1 over m with an inflation constant. No big surprise, something that one would expect, but proving it takes a little while. So that's this result. So this looks roughly like this.
There's a little h missing in that.
Yeah, it so happens that both little h and capital will finally connect it up. In this case, capital H, little h, the second moment, little h, and this are all moving at the same rate. So one can write this as well. We connect it with, so we can put a little h in there as well in the end, and that's what we'll do. Okay, so why does this help? This helps because the analysis of the previous equation comes down to thinking about how the sample size behaves and its inverse. Because you can think about this quantity purely in terms of the distribution of sample size because we've connected it up. Okay, and that's what's very useful. Okay, so this result essentially says, okay, it's sufficient to just think about the inverse of the sample size. So now, can we quantify the distribution of sample size? Well, let me show it to you in the form of a picture. It so happens that asymptotically what happens is you can quantify the sample size essentially asymptotes around h raised to the power eta. Well, think of eta as just 2. It's just inflated 2, but let's just think of it in terms of 2. This sample size right here, the amount by which it is exceeding 1 over h squared where little h is a true function value, constant times h raised by negative 2. It concentrates right on h raised by negative 2. Okay? And that's essentially what this theorem is saying. So this is kind of useful, again, going back to this result right here, because if this is looking roughly like 1 over m, and m is also, just concentrating of 1 over h squared, so to speak, and this guy is looking like 1 over h squared, or h squared, then these two are in lockstep. Okay? So it's about thinking about this quantity, and then we are asking for the distribution of capital M. Capital M looks very much like 1 over h squared roughly, and so these are kept in lockstep. Remember, little h is the actual quantity that you're trying to estimate at a particular x. So m is actually degenerating or going off to infinity at this rate, as k tends to infinity. So this distribution has been quantified this way, and so you can talk about the expectation of mk and mk inverse, which is what we do here. So notice here that expectation of mk inverse looks very much like h raised by negative 2 with an inflation constant. All right? The same can be done with mk as well. These two are constants, really not crucial, but we do think that they actually coincide. And again, to give you a little bit of intuition, little h squared is a crucial quantity. H, as k tends to infinity, h of xk is going to x star, and we're doing root finding. So h of xk goes to 0. And the question is, how are we choosing our sample sizes? Well, we said the error due to sampling is roughly of this order. The squared error due to sampling is roughly of this order. And this guy is roughly of the order h raised by negative 2. So those two are in lockstep. Okay? And so that's essentially why it helps us. So we put this all together now. So suppose I say work. I have to quantify work in this particular context. The total amount of work that I do is a summation of all of the sample sizes, right? Very unlike stochastic approximation. Stochastic approximation, the amount of work that I do up until the kth iteration is simply k. The amount of work I do here is simply the sum of all of the sample sizes. Now, this goes back, the first part of this main result goes back to one of the things that I pointed out earlier. We have the sequence called nu sub k, which I'm calling the escorting sequence, which helps us get to the vicinity of the root. It so happens that as k tends to infinity, the probability of capital M sub k exactly equaling nu sub k infinitely often is 0. So the trajectory that you need to think about is, as I get closer and closer, there is a lower bound that I'm imposing on the sample size. It is never hit. So in other words, the rule due to the adaptive sampling is almost always greater than the artificial rule that I imposed through nu k. Okay, so the likelihood of it actually exceeding nu k is infinitely often is tending to 1. Once we have that, we can show this result. This is reminiscent of the 1 over square root of work result, which is, this is the error. The error times the work raised by 1 minus 2 epsilon. We were hoping that this error would be of the order of 1 over wk, but instead we have a 2 epsilon right there. So it's a slightly weaker result. They're not able to converge right at 1 over square root of wk, but instead it's slightly slower, but this epsilon is an arbitrarily small constant. So this is, because of this, the wastage due to these guys adds up to very little. Okay, that was a key problem earlier because we artificially imposed a lower bound on the sample sizes. This is saying that lower bound doesn't matter because it hardly ever happens as you're going closer and closer. This is saying, okay, if it hardly ever happens, then all that matters really is the adaptive sampling rule that you've imposed. And we have shown that the error is roughly of the order of 1 over m, expectation of 1 over m, and that's this guy, and so this just works out to be order 1. So this is the main efficiency result that you're actually retrieving the order 1 over square root of work associated with adaptive sampling. And this is another a tangential result. It so happens that if you sample anything other than geometrically in the limit, your anything slower than geometrically, it so happens that you can never achieve efficiency at this site. Okay, so this is an illustration of how these sample sizes typically look when you actually implement this on a real problem. On the x-axis, I have iteration number. On the y-axis, it's the total it's the actual sample size that was incorporated, and this is a realization from a global optimization problem on on a online classified problem. And this is kind of how it typically looks. The red line right here is the new case sequence. It escorts you to the vicinity of the root, and as you're getting closer and closer to the root, the sample size actually increases. Okay, and then because we're doing global optimization, it just gets thrown out, and when it gets thrown out, it goes far away. And thereafter, it's kind of until it reaches the vicinity of another root, potentially, it is being governed by the new case sequence, which is the lower bound. So it travels right on it, and then it gets closer to another local minimum, where, for example, the sample size is forced to increase because of your adaptive sampling rule and goes up again. Exactly the sort of behavior that we wanted to see right in the first place. Okay, so the main insight, again, is you have to sample. The main insight of the heuristic, for example, is you want to sample until the standard error estimate of the object being estimated within the recursion is in lockstep with the estimate itself. So if there's one takeaway right here, it's this one. The standard error is in lockstep with the estimate itself, with a lower bound, and we actually add an inflation parameter here, primarily because you want the sample sizes to degenerate to infinity as you're getting closer and closer. In fixed width confidence intervals, or in proportional width confidence intervals, you usually have a parameter that goes down to 0. That's the way the sample size actually degenerates to infinity, so to speak. In this case, it is like a proportional width confidence interval, but the only catch is that the point at which you're actually computing a mean or a confidence interval is itself actually going to 0. The function value itself is going to 0, very unlike traditional proportional width confidence interval. So you have to artificially inflate it using this factor m raised by epsilon. And that's why we need to impose this. Under these conditions, nk goes off to infinity. So this is an artificial effect. This is an artificial effect that never comes into play, that doesn't come into play asymptotically. This guy is needed to make sure the sample size degenerates to infinity. And the rest is basically proportional with confidence intervals. Okay. Like I mentioned, the escorting sequence UK is needed to bring iterates to the vicinity of the root. The coercion constant epsilon is needed, unfortunately, to make sure the sampling error drops at the requisite rate. Generalization to faster recursions. Now, everything that I've said thus far assumes that the underlying recursion is actually going linearly, meaning that it is, notice here, that this is a linearly converging, this is this sequence right here, because of strong convexity, I'm assuming that the underlying recursion is linear. If you have sublinearly converging recursions or superlinearly converging recursions, one might ask, okay, what would you do with your sampling rule? And that will show up in the root, or in this quantity right here. Instead of actually having square root of m here, you will essentially be having a different power. or you can actually put a different power in here. And that will depend upon what recursion you're using. If you're using a superlinearly converging recursion, you'll put a power there to make sure that you're actually sampling at a higher rate. And for sublinearly converging, you'll actually put a lower power, so to speak. And that should show up here. But this rule is for linearly converging recursion, so to speak. Okay. Incorporation of bias estimators, non-stationary recursions. By non-stationary recursions, I mean instead of a capital H, if your recursion itself is varying across iterations, so you have a capital H sub k, things will, it seems like we should be able to do something similar. But the idea is pretty simple. Let's quit there.
Okay. Thanks very much. Yeah. Question?
I'm sort of thinking of what you're doing. You basically, at every step, you estimating some sort of a derivative of gradient, right? Every
Sure,
point in
sure.
some way or the other. Sort of as you get closer and closer to x star, right? Sort of you keep estimating the derivative basically near the same point, right? Or somewhere not far from it. So doesn't it sort of make sense instead of at every point just trying to re-estimate it from scratch? So somehow to reuse some of the old information?
Yeah, yes. I agree. But the point is, if all of these vicinity, if the points in the vicinity have used, so I agree with your idea, but this sample size right here, the estimate essentially should, in some sense, it has to become consistent. You need to, your derivative estimate has to, your sample size has to go off to infinity in effect. Okay, so it can be combined with the derivative, with averaging these derivative estimates. So one could imply that. In addition, this effect right here, what happens to capital H sub, this capital H will essentially become capital H sub k in that context. And so that's because you're actually utilizing estimates from previous iterations. So one could potentially do that. Sure. Yeah. Shane?
So the epsilon that's in there, I presume you can control that. You can squeeze that down, but in doing so, you probably have to pay a price with your escorting sequence.
I think you'll have to pay a price with the variance of your capital M. Because
I didn't care about that thing.
really.
Variance of sample size? Why would I care about that?
So because what will happen here is, I think you want, let me show you here, this result right here. This guy. The variance has to be bounded in order for expectation of m raised by -1 to be in lockstep with expectation of mean square. Okay? So if epsilon is, epsilon 0, for example, it so happens that the variance of mk is actually, the variance blows up. And so you don't have your expected error in lockstep with the expectation of m inverse. So we need to artificially impose this epsilon bound, so to speak, epsilon rho, in order to make sure these two are in lockstep. So essentially a way to, you don't have this issue in a situation where, let's say, this is a very different type of a proportional with confidence interval, because imagine a situation where you're trying to construct a proportional with confidence interval in a situation where your mu itself is 0. Usually the parameter, this parameter C is what goes to 0 in sequential proportional with confidence intervals. You don't have that, and you assume that mu is greater than 0 there. So you have a very, very different case in this context, and because of that, your variance blows up. The variance blows up, you have to stay away from that fact, and the way we do that is by imposing epsilon. Mu sub k is a way to actually bring you closer, because all this theory on proportional with confidence intervals is valid only asymptotically. If you're starting really far away, in order to get you close to the vicinity of the root, you need to do something. And so you need to impose it, but it so happens that asymptotically it doesn't play a role thereafter. It gets you to the vicinity and then walks away, so to speak. The same.
Following up on Shane, so how do we choose epsilon in practice? What is the good recipe for it?
Great question. I do not know. I don't know how to choose epsilon. We are working on a CLT sort of a result, a final result, so to speak, that will help us, choose epsilon. It will depend. Epsilon will affect the asymptotic, variance parameter that shows up in your CLT. Okay, and based on that, we are hoping that we'll be able to choose a particular epsilon, but we don't know at the moment.
So I have my own question now. So going back to this Nocedal result that you pulled out, it looks like in order to do that check, I need to know H, but I don't. So looking at their inequality.
Actually, you don't need to know H. Let's see. You're referring to this. So Nocedal's result basically says that if this error is less than or equal to C times capital H, you're saying that, I see what you're asking. You're saying that you don't know this error because you don't know little h.
Yeah, to check that, we need to
Right.
know H, right?
So they, in the unbiased case, the expected squared error is exactly equal to the variance, and you can estimate the variance. So you can estimate this quantity. So you're right. You don't know little h, but you can estimate this error through your variance estimate. This is exactly what we do as well.
So in Polyak recurrent averaging for stochastic approximation, that's sort of viewed as a safeguarding approach that seems to help these procedures. Is there an analogous idea here, or are you going to approach the root from one side?
So Polyak averaging is about averaging iterates, right? So this is about given a particular point you sample.
Right, but can you do that here as well? Or should you?
So that is related to the, I think so. I think that's a really good idea. I think we could do, in addition to whatever we are doing, we could take the iterates and average them as well. Although it's not clear. It's I don't know what gains we'll get in terms of the convergence. Polyak did that because she wanted a way by which Anatoly Jurinski, sorry, Polyak wanted a way by which to actually increase the step sizes, right? And so instead of using the 1/k sequence, he used the 1/k raised to alpha sequence. And then he achieved the, convergence rate, the order 1/k. Here, you're already achieving the order 1/square root of work. I don't know what more we could achieve, but it's possible that we could remove the epsilon by averaging. Not clear.
Okay.